Hello guys, in this lecture we're going to continue what we were discussing last time in terms of work and kinetic energy. And last time basically what we said is that we said the work is equal to the change of kinetic energy in a system, right? Today we're going to come up with a new term which is power, and basically power is going to be equal to the rate of change of work with respect to time. Well, what is work? Remember that work is equal to what? Is equal to the integration of F multiplied by ds, right? And we said, for example, if you have an object, right, that has a mass m, and you are, lifting that object by a distance h, then what is the work? The work is going to be equal to minus mgh. So here we're basically looking at the work of the gravity, right? If I had a force basically that was also applied on that object as it moved that distance, then the work of that force F is going to be equal to what? F times h, right? So work is associated with a given force, right? And now we want to look into the power of a given force, all right? So power is basically the rate of change of work with respect to time. If I do that, then what is the rate of change of the work is going to be equal to F times ds, right? Here, assuming basically we are projecting along ds, right? These are applied in the same direction. So F times ds is my d work, right? So d work, you will simply remove that integration and you divide that by dt. So it's going to be F times v. So power is an instantaneous value of force multiplied by the velocity. All right. So here's an example. If I have an elevator, right? Let's say you are working on, sizing up the motor that would actually lift the elevator. So if you do a quick free body diagram on elevator, we know we're going to be basically putting it with a force T. It has a weight of mg, and then here it has an acceleration diagram. It has ma, right? So summing the forces in a vertical direction, is going to give me T minus mg is equal to ma. So my T is equal to mg plus a. So what is the power of this force? So we said the power is equal to force times velocity. All right. So the power is going to be equal to T multiplied by the velocity. Well, what is T? I know what's my T. T is going to be equal to m g plus a multiplied by the velocity. All right, so depending on the acceleration that you want to impose on your elevator, like how fast you need to increase the velocity, and also multiplied by the velocity, you will actually get the power. All right, and the reason why I'm saying this power is instantaneous is because you actually have that velocity term, right? So it's dependent on the current state of the elevator. If the elevator is not moving, then what is the power of this tension? It's zero, right? Because this tension is not causing that elevator to move. So in that case, the power of that tension would be zero. All right. And then what I want to tell you guys is since we described power, then the next thing is we're going to talk about is efficiency, right? So here, when I'm looking at the power, so this is the power needed to create this or to sustain this movement or to sustain this acceleration, and obviously, the weight of the elevator, and to move the elevator at that velocity. So this is the output power of the system. So this is the raw mechanical power that I need to deliver to the system. But regarding the motor, sometimes the motor would actually have an efficiency, right? So the efficiency is given by P out over Pn. And when I'm actually calculating this power, basically I'm calculating the output power that needed to be delivered. So I need to be able to produce that. So what would be my input power is basically I'm going to divide the output power by the efficiency, and the efficiency is less than 1. So Pn is P out divided by efficiency. And if the efficiency is 0.8, basically you're going to divide whatever output power by 0.8, and then that is your power of the motor. And why are we really talking about power here? The reason why we are talking about power is, oftentimes in your career, you're going to end up, you might be working on a construction system, or, a pulley system, or whatever it is, or a pump, oil pump, whatever it is. And you want to be able to convert between uh, um, uh, different systems, for example, or to be able to size up the motor correctly to your application. And sometimes you could be dealing with a combustion engine, you could be dealing with an electrical engine, and etc. And all these basically are rated based on their power. They are not rated on, mainly are rated by power. So you will have, for example, like in the case of our elevator, let's say we obtain the instantaneous power, we can also obtain the maximum power. The maximum power will occur at acceleration, when the acceleration is most at startup and at that velocity, right? So you can calculate the maximum power, and you want to be able, your motor that you are getting has to have a power that is greater than your maximum power, all right? And ultimately the units of this will be in watts, right? So if you have 1,000 watts here, then you can go, if you want to look into electrical motors, you can find an electrical motor that has, 1,500 watt or 1,200 watts, and you multiply that by the efficiency of the motor, and you want that to be still greater than the maximum power that is in your system. Okay, guys, so this is what we have here. And now what I would like to do is I'll just quickly go over our lecture on power and efficiency. So this is our power. And oftentimes, like I said, we need to be able to convert or we need to be able to estimate the power that is generated by a machine, or the power required to actually drive a machine, the power of an engine, motor, etc. And the purpose here is to be able to calculate the mechanical power and the mechanical efficiency. This is an example of an elevator, right? The elevator, you are pushing an elevator with a force F, and that force F is not only equal to the weight, it's equal to the weight in addition to the inertial acceleration to be able to accelerate that elevator, right? And the power is going to be equal to F times V. Pretty basic. All right, so that is nothing here. So this is a derivation, which I already described. Power is the rate of change of the work with respect to time. If you differentiate that, you're going to obtain force times velocity. In terms of units, the unit of work is a unit of power is going to be in joules per second or Newton meter per second. If you were dealing with a bridge system, it's going to be given to in horsepower, where 1 horsepower is equivalent to 550 feet per pound per second. And this guy is equal to 746 watts. So if I give you, bridge units, you should be able to get the corresponding wattage to it. And like we said, efficiency is output power divided by the input power. The output power is the power that you actually need to realize on your actual system, and the input power is a power that is actually coming from your source of power, which could be, solar energy, wind energy, combustion engine, electrical engine, whatever it is. All these are rated based on their wattage. All right. And the efficiency actually also apply for the energies. Why? Because we know the power is the rate of change of the energy. So, if you integrate the top and the bottom, your efficiency still holds also on energy. So to be able, procedure for analysis, the first thing that we have to do is free body diagram. Why do you need to do a free body diagram? Because you want to get the force that you actually need, right? To move the object, or to move the inertia, basically. So you do the force, and then you look at your motion profile. What is the velocity that you are using to drive this? With what velocity? So you multiply the force by the velocity, and it is instantaneous. And this is how we can get the power, and ultimately we can get the power. We can use the efficiency to calculate the input power that is needed to drive the system. Okay, guys, so here we're going to do a quick example. We have this 2 megagram car, which is 2,000 kilogram car, and its velocity is constantly increased from rest to 25 meters per second in 30 seconds up the inclined road. So here the speed is uniformly increasing. I think that means the acceleration is constant, right? So your velocity starts at 0 and the velocity ends up as 25 meters per second. So V is equal to AT here, right? Where A is the acceleration. We can get the acceleration V is equal to AT, so A is equal to V over T. We can do that. And then we need to find the maximum power that must be supplied by the engine, which operates with an efficiency of 0.8. And then we need to find the average power. All right, let's do that. So let me use that for a bit here. And let's do that. So this is our, so this is our car, and this is our slope, and we have basically a 10 to 1 here, 10 and 1. So this is my theta, so we can quickly get theta, and we need to get the maximum power. So what is the power basically? First of all, the power we said is going to be equal to force times velocity, right? What is the velocity? The velocity is actually increasing from 0 to 25. So velocity is equal to A times T, right? What is A? Well, we know that we're going to reach 25 meters per second. So 25 is going to be equal to A times how much? Times 30, right? So we reach a velocity of 25 meters per second after 30 seconds. So we know V is equal to AT. So A is going to be equal to 25 over 30, or V is equal to 25 over 30 T. 1 time is equal to 0, your velocity is 0. 1 time is equal to 30, your velocity is going to be equal to 25 meters per second. Okay, now we need to find the force. So we get the velocity as a function of time. Let's get the force as a function of time. How do I get the force as a function of time? Well, somehow we are pushing the car with a force F, and it has a weight mg. And on the acceleration diagram, it has an ma, right? So if this angle is theta, I believe this angle is theta. So if you sum the forces along the motion, what would be the force F? F minus mg sine theta is equal to ma, right? So F is equal to m a plus g sine theta, and here is meters per second squared. Well, we know the force is basically going to be constant, right? So the force is going to be equal to the mass, which is 2000, multiplied by the acceleration, 25 over 30, plus 9.8 sine 30. So theta is how much? So inverse 10. So theta is very small here, right? Tangent 1 over 10. So theta is equal to 0.1 radian, or very close to 0.1 radian, right? So for very small theta, so tangent theta is equal to 1 over 10 or 0.1. For very small angles, tangent theta will actually be equal to theta, right? Or you can do the inverse tangent, right? So which is equal to how much? Which is equal to 1 over 10, which is equal to 0.1. So theta is roughly equal to 0.1 radian. 0.1 radian, right? So this is my force. And the force here is basically constant. And if you do that, you will see that if you do the mathematics here, I believe, crunching the numbers, it will be 36 to 2.7 Newton. So my force is constant. This is my velocity. So let's get the maximum power. So the maximum power happens at the maximum T, right? So P max is equal to F times max velocity, right? Which is equal to how much? 36 to 2.7 multiplied by the maximum velocity, which is going to be equal to how much? 24. And I believe if you do this, you will end up with 90,567 watts. And by the way, the maximum power doesn't have to be F, doesn't have to be force times V max. It is actually this whole thing, the maximum of this guy, maximum of the product, right? And the best way to get the maximum of the product is by actually plotting both of them. Well, in the next part, they actually ask us about finding the average efficiency, but the average power. But before we do that, this is a maximum power that has to be delivered to the car. So this is a mechanical power. How about the engine? What is the power that the engine needs to deliver? Well, the input power, right? Or let's talk about the efficiency first. So okay, here. So the efficiency is equal to P out over Pn, right? So this guy is my P max out. So Pn has to be equal to P out over N. So power of the engine is equal to 9567, divide that by 0.8 watts. All right, guys, so this is very important. Now, if you want to get the average power, one thing that I like to do when I'm dealing with power is to actually plot everything together. You know what I mean? So we can do this. We can plot the force, just force, one force. We can plot the velocity, and here we can actually plot the power. Okay, so what is the force that is done during that movement? And that move starts at 0 and it ends at 30 seconds. So these are 30. So I think during that move, the force is constant because it's equal to G sine theta plus mg sine theta plus ma. And the force we said is going to be constant throughout that movement. So it's the horizontal line. And it's here. So this is my force. Now, how about my velocity? We said the velocity will start at 0. And at 30 seconds, it's going to be equal to 25. So this is my velocity. It's going to be 25 meters per second. And now how about the power? The power is a multiplication of these two lines, right? So the maximum power is whatever the maximum happens here. And then if you multiply this guy with this guy, you know, this guy is 0. So your power has to be 0 initially, but ultimately it's going to end up here. And this is my maximum power. What is my maximum power here? My maximum power is already given to me. We already calculated that, right? And you just multiply this guy. You multiply 25 by 3622. If you do that, you will get the number that we described earlier, which is 9567 watts. Now a question, what do you think is the area under this curve? What is the area under the power? Well, we know power is equal to what? D work, right? dt. So work is integration of power dt, and from 0 to time t. So from 0 to time t, we can actually get the work done, the mechanical work basically that is needed. Okay, if you want to find the average power, so what average power you have here, so you actually get the same work. So this area has to be equal to the other area, right? So let's say this is my average power. In that case, my average power multiplied by this distance, 30, right, has to be equal to the whole work done, which is equal to P max, this is the maximum power, right, P max, multiplied by 30. So this is triangle. I can do P max multiplied by the base, which is 30, and then divide that by 2, right? And 30 and 30 will cancel out. So my average power is equal to P max over 2. This is the average mechanical power, right? If you average input power of the engine, it's going to be P average on the, you know, the mechanical power here, and then you divide that by the efficiency, right? So this is the average that is actually the average power needed to, the average power that is actually, you know, an average moving the car, and this would be the average engine of the motor, average power on the motor. So P average here, divide that by the efficiency. Okay, guys, let's do one more problem. And here, basically, what we have is we have a hoist system, and the motor basically is lifting the 60 kilogram crate at a constant velocity to a height of 5 meters in 2 seconds. Right, so it's 25 meters in 2 seconds. And if the power of the motor is 3.2 kilowatts, we need to find the motor efficiency. How do we do that? It's pretty basic here, right? So if you look into it, so this is your mass. It has mg, it has a tension T, and it's moving with a constant velocity, right? So yeah, acceleration, there's no acceleration. So T is equal to how much? mg, right? So what is the output power? Is going to be equal to T times V. It moved to the constant velocity. So mg times, what is the velocity here? 5 meters per 2 seconds. So 5 over 2, right? What is m? 60 times 9.8 times 5 over 2. Right? This is the output power. This is the mechanical power. برجع بقول لك انه power of the motor, power in of the motor is 3.2 kilowatt. Let's call it power output here, right? So what is the efficiency then? N is going to be P out over Pn, right? So P out is how much power we basically got, right? So tension times velocity is equal to this. So 60 times 9.8 times 5 over 2, divide that by 3.2 kilo times 10 to the 3, right? And this is how you basically get the efficiency. Okay, if you multiply 60 times 9.8 times 2.5 divided by that, the efficiency would be 0.46. All right, guys, so that is it regarding this lecture. Any questions, guys, on this material, please do feel free to email me, and I'll be very happy to set up a one-on-one Zoom call, or if you have a group, we can do another Zoom call as well. Okay, guys, that's it for this.